Okay, kids, we're back today, and we're going to pick up on our discussion on waves, and we're going to introduce a very important equation in the study of vibrations, waves, particularly the universal wave equation. That means it's an equation that works on waves, not just one wave or two waves, all of the waves. It's universal. The speed that a wave travels, you can find it, you can calculate it by measuring the distance it travels and the time it took to travel that distance. Ooh, remember that old equation? Very simple one. Speed is equal to distance over time. How does that apply to a wave? What distance are we talking about exactly? What time frame are we talking about exactly? We need to figure that out. And when we do, we will understand the universal wave equation. Okay, so we're back at this simulation. It's very helpful. And we want to figure out a way of calculating the speed of a wave. And what we're going to do then is figure out the distance it travels through the medium, through the material. And let's do that. That'll be better. And in order to figure out or to measure the distance, we need a ruler. So we got a ruler right here. And we want to also know how much time it takes to travel a particular distance. So we've got a stopwatch right here. All right. Now we're going to do this very slowly in slow-mo. Okay. So let's start the wave step by step. Okay. So 0.01 second went by. It's hardly moved, but that's how slow we're going to do this so we really get the point across. So the vibration has gone through, that's about right there, 1 amplitude. So the first half of the crest has been produced. At this point, the wave has only really reached just over a centimeter, and it's taken 0.16 seconds. All right, so let's keep going. So now the wave, the vibration, I should say, has gone through up amplitude, down amplitude, two amplitudes, and an entire crest has been created. And it's about 0.33 seconds. All right. And the wave has gotten to, oh, gee, I don't know, just over 2 centimeters. Let's keep going. There we have it. It's pretty darn close, anyways. Maybe another one. Yeah. Okay. So now the vibration's gone up, down, and down, 3 amplitudes, and the wave has gone through a crest and half of a trough, and it's gotten to, I don't know, just over 3 centimeters forward from the start position. So this is the distance it's traveled, and this is how much time it took. So let's go forward. I think we're almost there. Maybe one more. Okay, let's leave it at that. So now the entire wave has gotten to here, which I don't know, maybe is about 4. Let's bring the ruler down and line it up. It's around 4.2 centimeters. So that's how far the wave has traveled. So that's the distance that the wave has traveled. But lo and behold, I know the name of this distance. This distance is the length of a complete wave, a crest and a trough. So the distance that the wave traveled is the wavelength, our friend Greek letter L, lambda. So the distance it traveled is the wavelength. And here's the time that went by, 0.66 seconds, all right? But that's not just any time. That's the time it took for the vibration to go through 1 amplitude, 2 amplitudes, 3 amplitudes, 4. That's a complete cycle of one wave. What do we call the time for a complete cycle? We call that period. So yes, we know the distance it traveled. Yes, we know the time it took to travel that distance. But it's a special distance. It's the wavelength. And it's a special time. It's the period. That's very important. That's very powerful. Let's get back to our note. So we're back to our note, and we know that speed is distance over time, but it's not just any distance, it's wavelength. It's not just any time, it's the period. So the speed of a wave then equals its wavelength divided by the period of the wave. This is one version of the universal wave equation. Here's a new equation for you. Make sure you put it on your equation sheet. Next, I want you to remember one of the things we discussed a while ago, that and frequency and period were reciprocals of each other, or inverses. So that means 1 over period is equal to frequency. Remember that from our early definitions of frequency and period. If you don't remember, you'll have to go back and look at your notes, please. So instead of writing the universal wave equation like this, let's write it as, instead of being divided by period, let's have it being multiplied by the inverse of period, 1 over period. All right? Because remember, if you divide something by a quantity, it's the same as multiplying by the inverse. If you divide something by 2, it's the same as multiplying by half. If you divide something by 3, it's the same as multiplying by a third. If you divide something by t, the period, it's the same as multiplying by 1 over t. But remember that the 1 over t, 1 over period, is nothing more and nothing less than frequency. So the second way you can write the universal wave equation is the speed of a wave is equal to its wavelength multiplied by its frequency. And we remember from the other day that the speed of a wave depends on the material it moves through and the condition. If you remember, I changed the tension in the spring, and the speed of the wave change. So that has an important impact on that. So we're going to focus all of today's work on these two equations. They are two different versions of the same equation, the universal wave equation, and we use that simulation to help us understand that. And if you want to go back and use the simulation, I'm going to have the link. I'm going to give you some questions to do, some reading to do, and hopefully we'll get this all straightened out. Thank you.